Heat death. The universe doesn't end in fire, it ends in silence. Right now, every star, every galaxy, every particle of dust is radiating energy outward, and none of it is coming back. That's the whole story compressed into one sentence, and it will take longer to finish than anything else on this list. In 100 trillion years, the last new stars will form and burn out. Star formation stops entirely because the hydrogen gas needed to build new stars finally runs dry across the entire observable universe. In 10 to the 40th years, even the dead husks of stars, the white dwarfs and neutron stars, will have either decayed or been flung out of their galaxies entirely by chance gravitational encounters, drifting alone through an emptier and emptier cosmos. Black holes become the last real structures standing, and even they don't last. They slowly evaporate through a process called Hawking radiation, first predicted by Stephen Hawking in 1974. A stellar mass black hole takes about 10 to the 67th years to fully evaporate. A supermassive black hole, billions of times the mass of the sun, takes roughly 10 to the 100th years. That number is so large it has its own name, a googol. Written out, it's a 1 followed by 100 zeros, a number bigger than the count of atoms in the observable universe, used here to measure a single unit of time. But here's the thing. Even after every black hole is gone, the universe keeps expanding. Space keeps stretching. Temperature keeps dropping, asymptotically approaching absolute zero, but never quite touching it, forever chasing a limit it can never fully reach. This is called the big freeze or heat death, and it is currently the leading prediction in mainstream cosmology, the scenario the data points toward most consistently. Entropy, the measure of disorder and energy spread in a system, will reach its maximum possible value. No more energy differentials, no more temperature gradients to power any process. No more chemistry, no more thought, no more light bouncing between anything. Here's the part that should genuinely bother you. Heat death isn't a violent apocalypse. It's the opposite. It's the universe running out of interesting things to do forever with time left over to prove it over and over into an infinity that never resolves into anything new. Let that sink in. An eternity of nothing, stretching infinitely into a future with no end and no purpose, no observer left to even notice the silence. Consider the numbers side by side. The universe is 13.8 billion years old today. Heat death's final stage arrives roughly 10 to the 100th years from now. If the current age of the universe were shrunk down to one single second, the wait for heat death would still stretch out longer than any timescale a human mind can meaningfully hold on to. We are not partway through the story. We are in the first immeasurable instant of it. But heat death assumes something specific about how the universe's expansion behaves over unimaginable timescales. What if that expansion doesn't just continue, but accelerates without any limit at all? Big rip. If heat death is the universe fading quietly into silence, the big rip is the universe getting torn apart at the seams, violently, in a finite and calculable amount of time. This scenario depends entirely on dark energy, the mysterious force making up about 68% of everything in the universe, the force pushing galaxies apart faster and faster with every passing billion years. If dark energy has a property physicists call phantom energy, meaning its repulsive strength actually increases over time instead of staying constant, the outcome becomes catastrophic rather than gentle. First, galaxy clusters get pulled apart. This starts subtly, over billions of years, as the space between galaxies stretches faster than gravity can hold them together across those distances. Then, individual galaxies unravel one by one. The Milky Way itself would come apart, stars flung away from each other as the fabric of space between them expands faster than light itself can bridge the widening gap. Then it gets personal, and it gets fast. Around 60 million years before the theoretical end date, solar systems would be ripped apart, planets torn from the stars that have held them in orbit for billions of years. About 30 minutes before the end, planets themselves would be shredded, their own gravity no longer strong enough to hold them together against the runaway expansion of space itself. Here's the fact that changes everything. In the final fraction of a second, the expansion becomes so violent that it rips apart atoms themselves. Electrons torn from nuclei, quarks torn from protons. Even the electromagnetic force that binds an atom's own structure together loses the fight. The Big Rip ends not with darkness, but with the total simultaneous destruction of the very concept of structure at every scale at once, from galaxy superclusters down to subatomic particles, all in the same instant. Current measurements of dark energy don't strongly support phantom energy behavior, so most cosmologists rank this as a lower probability scenario compared to heat death. But the data isn't fully settled, and the error bars on dark energy's exact behavior remain wide enough that it hasn't been ruled out. If you want a universe that ends in physical violence rather than quiet fading, this is the one. Not with a whimper, but with everything, everywhere, tearing apart at once, on a schedule you could theoretically calculate down to the second. Some estimates, based on current dark energy models where phantom energy is allowed, put the Big Rip roughly 22 billion years from now, a timeline almost embarrassingly close compared to the Google scale numbers everywhere else on this list. Close enough that if it's real, it would arrive while red dwarf stars, the longest lived stars in the universe, are still only middle aged. But not every ending scenario predicts eternal expansion. Some scenarios run the tape backward instead. Big Crunch. This is the universe's oldest theorized ending, the mirror image of the Big Bang, and for decades it was the default assumption before better data came in. In this scenario, the expansion of the universe eventually slows, stops, and reverses course entirely. Gravity, given enough time and enough total mass, wins the tug of war it's been losing since the beginning. Galaxies that have been rushing apart for tens of billions of years begin, instead, to fall back toward each other slowly at first. The night sky would begin to brighten, not from starlight, but from the cosmic microwave background itself, heating back up as space contracts and ancient radiation gets compressed into smaller and smaller volumes of space. Temperatures would rise the way they fell after the Big Bang, only running in reverse, like footage played backward. Stars would be crushed together under the collapsing weight of everything around them. Galaxies would merge violently, not in the slow gravitational dance we observe today between the Milky Way and Andromeda, but in a rapid, accelerating, inescapable collapse. In the final stages, the entire observable universe would contract from billions of light years across down to the size of a single atom in less time than it takes to read this sentence out loud. Here's the fact that changes everything. For a big crunch to happen, the universe needs enough total matter and energy for gravity to overcome the expansion permanently. And every precise measurement taken since the 1990s shows the exact opposite trend. The expansion is accelerating, not slowing down. Current data makes the Big Crunch one of the least likely outcomes based on everything we currently measure about the cosmos. And yet, it hasn't been completely ruled out because we still don't actually know what dark energy is, only what it currently appears to do. If dark energy's strength weakens over cosmic time instead of staying constant, contraction becomes possible again, even likely. The universe that began in a single infinitely dense point could, in theory, end in the exact same way it started, which raises an unsettling question worth sitting with for a moment. If the universe can end where it began, could it also begin again, immediately, out of its own ending? Einstein himself briefly favored a static, cyclical universe before observational evidence forced him to abandon it, calling his resistance to expansion his biggest blunder. The Big Crunch was, for decades, considered the more scientifically respectable option, right up until the data stopped cooperating. Big bounce. Here's the twist that some physicists find far more elegant than any permanent ending. What if the Big Crunch isn't a death at all, but a rebirth in disguise? The Big Bounce model proposes that a universe undergoing gravitational collapse doesn't compress all the way into an infinitely dense singularity, the mathematical wall where our current equations simply break down and stop making sense. Instead, quantum effects operating at extremely small scales create a repulsive pressure that halts the collapse just short of infinity, and the universe bounces back outward into a brand new expansion phase. A new Big Bang, in effect, indistinguishable in its earliest moments from the one that created us. Loop quantum cosmology, one of the leading frameworks used to explore this idea mathematically, suggests that space itself has a minimum possible size, a quantum floor it physically cannot be compressed past, no matter how much mass is pressing down on it. When contracting matter and energy hit that floor, the bounce happens instead of a singularity forming. This isn't just speculation for its own sake either. It's a genuine attempt to solve a real, unsolved problem in physics. General relativity simply stops producing meaningful answers at a singularity, so physicists need some other framework to describe what actually physically happens at that extreme. Here's the fact that changes everything. If the Big Bounce is real, our Big Bang wasn't the beginning of everything that exists. It was just the most recent bounce in a cycle that may have been repeating for longer than beginning is even a meaningful concept to apply. Some versions of this model propose an eternal series of expansions and contractions, universe after universe, cycle after cycle, each one erasing almost all evidence of the one that came before it. We would be living in the debris of a previous universe's death, with no realistic way to prove it either way. There is currently no direct observational evidence for the Big Bounce, and it requires the accelerating expansion we currently observe to eventually reverse course, which directly conflicts with our current best dark energy measurements. It remains a mathematically compelling, philosophically fascinating, but empirically unconfirmed idea. But not every proposed ending requires the entire universe to contract first. Some endings could start in a single random point and spread from there at the speed of light without any warning at all. Vacuum decay. This is the ending that keeps some physicists up at night because, unlike every other scenario on this list, it could theoretically happen at any moment, anywhere, with absolutely zero warning. The premise starts with a strange, uncomfortable feature of quantum field theory, the possibility that the vacuum of space, the nothing that fills the universe between particles, isn't actually the most stable state it could possibly be in. Picture a ball resting in a shallow dip partway down the side of a mountain. It looks stable from where you're standing. It isn't the lowest point actually available on that mountain. If it gets nudged even slightly, it rolls further down into a deeper, more genuinely stable valley. Our vacuum might be exactly that shallow dip, what physicists call a false vacuum. They call the deeper, truly stable state the true vacuum. If a region of space anywhere in the universe spontaneously or through some extreme energetic event tunnels into that true vacuum state, a bubble forms at that exact point. Inside that bubble, the fundamental constants of physics are different from ours. The mass of particles, the strength of the fundamental forces, the rules matter is required to obey, all reset instantly to new values. Here's the fact that changes everything. That bubble does not stay contained where it started. It expands outward at the speed of light in all directions simultaneously, converting ordinary space into the new vacuum state as it goes, with nothing able to stop or slow it. Because it moves at light speed itself, there is no possible warning anywhere, ever. If a bubble started at the edge of the observable universe today, we would have zero notice before it arrived here, because no signal, no light, no information of any kind can outrun something already moving at the maximum speed the universe allows. Every atom, every structure, every law of chemistry within that bubble gets rewritten instantly and without exception. This isn't science fiction dressed up as physics. It's a real, published, ongoing concern in theoretical physics, tied directly to the precisely measured mass of the Higgs boson. Current measurements place our universe in a state that's metastable, meaning it's stable enough to have already lasted 13.8 billion years without incident, but not proven to be the true lowest energy state actually possible. The calculated timescale for this to happen naturally is almost incomprehensibly long, likely far longer than the current age of the universe itself, possibly longer than any other single scenario on this entire list. So don't panic, genuinely. But do sit for a moment with the idea that the walls of reality might have an expiration date we simply haven't reached yet, ticking down somewhere we can't see. Physicists have even given this hypothetical bubble wall a name the domain wall, the boundary between the world we know and the world with different rules. Some calculations suggest that if the bubble began far enough away, it could theoretically be moving toward us right now, and we would still have no way to detect it before the moment it arrives, because detection itself requires a signal, and nothing outruns light. If vacuum decay doesn't get us, and the black holes eventually evaporate the way heat death predicts they will, there's still one more piece of this puzzle left. What happens to ordinary matter itself, given enough time to work with? Proton decay. Everything solid you have ever touched, ever stood on, ever been made of, is built from protons and neutrons. We generally think of protons as permanent, unbreakable, the literal bedrock of all atomic matter. Some grand unified theories in particle physics predict they aren't permanent at all, just extremely, almost unimaginably patient about it. If protons decay, a single proton has some tiny non-zero probability of spontaneously breaking down into lighter particles, like a positron and a neutral pion, over an astronomically long timescale that dwarfs everything discussed so far. Experiments have already set firm lower limits on how long this would take, with current bounds placing the proton's minimum possible lifetime at over 10 to the 34th years, if it decays at all, under any circumstances. To put that number in perspective, the universe itself is currently about 10 to the 10th years old. We're talking about a process that, if it happens, wouldn't become statistically noticeable until the universe is a trillion times older than it is right now, this very moment. Here's the fact that changes everything. If protons do decay, it means ordinary matter itself is not eternal, not even close. Every rock, every planet, every dead star remnant left over after heat death has run its course would slowly, atom by atom, dissolve into nothing. Neutron stars and white dwarfs, the toughest, most durable surviving structures in a post-heat death universe, would eventually crumble as their constituent protons blink out of existence one by one, converting their remaining mass into scattered radiation. This would mean that even in a heat death scenario, matter itself doesn't get to last forever within it. It eventually joins the same fate as everything else around it, reduced to stray particles and radiation drifting through absolute cold, empty space. No experiment has ever actually observed a proton decay in real time. The Super Kamiokande detector, buried deep underground in Japan, has watched enormous tanks of ultra pure water for decades, waiting patiently for a single flash of light that would mark the moment, and hasn't seen one yet, not once. It remains a serious, well motivated prediction, not a confirmed observed fact. But if it's true, solid matter was always a temporary illusion, running on a clock so long it makes the lifespan of stars look like the lifespan of mayfly flies by comparison. The theory that first predicted proton decay, called grand unified theory, was also trying to explain something else entirely. Why the electric charge of a proton and the electric charge of an electron match so precisely, to an accuracy of better than 1 part in a billion trillion. Proton decay isn't a random guess bolted onto physics for drama. It's a side effect of an idea that's already doing serious work, explaining the universe we can see today. And if matter does eventually dissolve, and black holes do eventually evaporate, we're left staring straight at the true final chapter, the one nearly every serious cosmological model agrees on eventually, regardless of the path taken to get there. The black hole era and the dark era aftermath. Strip away every other scenario on this list, and cosmologists broadly agree on this much. Whatever else happens along the way, the far future belongs briefly to black holes, and then after that, to nothing at all. After the last stars die out, somewhere around 10 to the 14th years from now, the universe enters what's called the degenerate era, a period dominated by white dwarfs, neutron stars, and black holes, the dense, compact leftovers of every star that ever burned. As proton decay, if it's real, slowly dissolves the white dwarfs and neutron stars over the following tens of trillions of years, black holes become the last genuinely massive objects remaining anywhere, giving this entire stretch of cosmic time its name, the black hole era. Black holes, despite the name and the popular image of permanence, aren't actually eternal objects either. Stephen Hawking showed in the 1970s that they slowly radiate energy away and shrink over time, evaporating completely given enough of it. A stellar mass black hole takes about 10 to the 67th years to evaporate fully. A supermassive one takes up to 10 to the 100th years. That same Google figure from earlier. Here's the fact that changes everything. When the very last black hole in existence finishes evaporating in one final faint burst of radiation, there will be nothing left anywhere that can honestly be called a structure at any scale in the entire universe. Not a particle of ordinary matter, not a photon with anywhere interesting left to go, not a single meaningful gradient of temperature or density anywhere across an infinite, endlessly expanding volume of space. This final stretch of time is called the Dark Era, and it's less a single moment and more an ongoing condition, an eternity of maximum entropy, sparse stray photons, and lonely particles drifting through a cold, flat, structureless cosmos forever with nothing left to interrupt it. There's nothing left to happen, and there's an infinite amount of time available in which that nothing can continue happening. This is where nearly every model on this entire list, heat death, proton decay, black hole evaporation, eventually converges into the same final state, regardless of which specific path the universe takes to arrive there. Even the language physicists use starts to break down here. Time technically keeps going, but with no clocks, no cycles, no change of any kind left to measure it against, later stops meaning anything at all. So, of everything covered here, which ending actually wins? Based on current data, heat death, the slow fade into maximum entropy, is the scenario most consistent with everything we currently measure about dark energy and cosmic expansion. It doesn't require dark energy to suddenly change its behavior. It doesn't require the expansion to reverse course. It fits every observation made since the accelerating expansion of the universe was first confirmed back in 998. The Big Rip requires dark energy to behave in a way we haven't yet confirmed through observation. The Big Crunch and the Big Bounce both require the expansion to reverse, which directly contradicts our current measurements. Vacuum decay and proton decay are both real, mathematically grounded possibilities taken seriously by working physicists, but their timescales are so long, or their triggers so vanishingly rare, that they function more as footnotes appended to heat death than as genuine competitors to it. In practice, most of the roads we currently have any real evidence for lead to the exact same destination: black holes evaporating one by one, matter possibly dissolving atom by atom, entropy climbing steadily toward its absolute maximum, and a cold, dark, structureless universe stretching on forever with nothing left to fill it. If you had to rank them by confidence, it would look something like this. Heat death sits at the top, treated as the working default across modern cosmology. Proton decay and vacuum decay follow, real and mathematically serious, but unconfirmed by any direct observation so far. The Big Rip trails behind that, plausible only if dark energy turns out to behave in a way we haven't yet measured. The Big Crunch and the Big Bounce sit at the bottom of that list, elegant, historically important, and currently at odds with the data we actually have in hand. Here's the part that should genuinely bother you. All of this is almost certainly going to happen after every trace of human civilization, every human memory, every scrap of human meaning has already been gone for a length of time we don't even have a proper word for. The end of the universe was never really about us. It never was, not for a single second of it. We are a flicker, a few thousand years of noise, on a timeline measured in numbers so large they stop feeling like numbers at all and start feeling like abstractions. And yet, here we are on a small, wet rock, figuring out exactly how it all ends before we've even figured out how to get along with each other down here. Not bad for stick figures on a rock.